Okay, so very good morning to all of you. It's the last day of the workshop, and again, it's a pleasure to talk to you. So today is part 2 of the lectures for jets and machine learning. So yesterday, we sort of reached to a point where we introduced what are jets utilities as a quantum mechanical object, how exactly jet looks like, so on and so forth. And we sort of scratched the initial part of what is machine learning and what's not, and stopped at a point that jets are essentially best represented as a point cloud, and we saw many phases of representations of jets. Since there were few slides left out from yesterday, I will first cover those, which are like diving slowly into the machine learning world, given jet as the background data structure we have in mind. And then we will sort of go through some vast, let's say, major applications of machine learning in jet physics context. We'll try to see where the modern algorithms are applied and where the maximum advantage we are having. And then we will try to explore what are the future prospects of this. And of course, this is like a dialogue in the sense we will keep having discussions in between. So please feel free to stop me, make your comments, ask questions. Yeah.
Just had
nightmare? No, okay. Oh, okay.
Last class.
Yeah.
And, you mentioned that there are these non-linearities that come when you construct this
neural networks. Yes.
So is it like any non-interacting nonlinear system can be presented in
let's say any nonlinear system. Now the system can be some strongly coupled quantum system you build in the lab. It can be some stock market time series analysis. You just don't know that whether a stochastic system which is undergoing some dynamics which is highly nonlinear, how to map it.
And do you need a chaotic system or it is general, any nonlinear system?
Let's say the mathematical theorem goes as any nonlinear system. In fact, it's like how to map a chaotic system is a non-trivial task, and you have to really write down a neural network, train it carefully, and things like that. So I'm sure that if you train a neural network where the fluctuations of the systems are bounded and train the neural network on such a data, it won't work out of the box on a chaotic system. It cannot be.
Because UCD is intrinsically chaotic.
Yeah. Okay, good. So let's start. Here is the point. So I don't know, can someone just close that thing? I'm getting some extra amount of light. Nonetheless, let's move on. So yesterday, we sort of stopped at a point that we found a jet, which is a collection of particles, has many faces in the sense that given a jet, there can be an image-based representation, a set-based representation, a sequence, a tree, and a graph. And we will try to see if you want to write down an inductive bias on each such data structures, how do you actually do it, and then how you solve a practical problem. So let's start with this. Before diving deep into the networks, currently there are two classes of networks. One is something called particle net, which was built by people in CMS, especially Huilin Ku and Lucas Goskas. And on the other side, we on the Atlas side build something called GN1, GN2, etc. So I will come and discuss both such architectures, which actually played a pivotal role, say last 3-4 years, in training all the mainstream machine learning tasks. So we will try to understand how those things are going, but let's start with an easier one. First, when machine learning in 2014-15 were done on jet images, what was the idea? That if you have a one-pronged jet coming from gluon fragmentation or light parton fragmentation and take an average of jet image. So what do? the jets are depositing energy in calorimeters. You center a jet around its hardest particle and then just plot in the eta phi plane. And then you take a large number of ensemble of such that jet, do a pre-processing and take the average of the image. So you can see here from the pixel values that the hardest SID particle lies at the center, and then the other particles sort of in eta phi plane lies in a circular region. Whereas when you look at a hadronic decay of a W jet, then you see apart from the center, there is a secondary bulge maxima, which clearly shows that there is a two-pronged structure. Now, if you show this thing to a computer vision person who has never done any QCD, they will say, okay, you give me a bunch of such images and you tell me a truth label, and I will be able to write down a convolutional neural network, which of course has filters, things like that, which the weight parameter, like the parameters of the filters act as the weight parameters. One can train a neural network, and then such a neural network, if you show it an image, it will be able to tell you this sort of average image is coming from a W jet, this is coming from a top jet, this is QCD. So this was the first sort of birth of jet images, which became very popular. But then I also told you yesterday through an image that when it came to our real-life calorimetric application in the detectors are not uniform grid of pixels. Each layer have different structures. You have to incorporate that. And for that, you need to really go to a point cloud representation, where each voxel shape is important, but nonetheless, you can sort of make the representation global, that each voxel has certain amount of energy and a particular location, and you can use that information. So, yeah.
Those are jets structure?
These ones, yes.
Why the lines are?
Oh, this color part, it means, that means which one, like this part?
The black.
Oh, so the black is actually like extremized. So let me just take a little explanation of how this part is made. So what happens that if you have, let's say, our famous cylindrical detector, whatever fame it has gained, but it has like onion-like shape, multi-layered. Okay, then there is another layer. And so on and so forth. You can keep increasing layer. Now you think, here there is a hard scattered pattern, which eventually build a cluster of hadrons and photons, which are lying close by, and then they're releasing energy in this calorimeter. What will you see? Here, you will see some deposition of energy. Of course, one layer of calorimeter cannot absorb all the energies, so the shower will leak in the radial direction, and the next layer will also get some energy, and then there will be energy deposits in ecal, energy deposits in hadronic calorimeter. So what you have is like in a conical shape, some energy deposition is happening, which is multi-layered. Now what you can do, you can pre-process this energy deposit. How? Because this is sort of a grid stuff, right? These are on the surface of these cylinders, there are eta phi grids. So what you can do, you can ask, where is my maximum energy deposition? Now you can move all the energy deposition, taking that maximum SID as the center, and can do some scaling as well. Now you do it for every instance and sum it up and divide it by the number of such instances. So if you take that image, the average image, it is always by construction, this preprocessing construction, the hardest SID lies at the center. That's why when you stack them up, you see like sort of a dark region in the center, which essentially says that's where, on an average, where the maximum energy deposition is by definition, and the rest of the energy deposits are in its peripheries. Yes.
Sir, on saying average, you mean that you can take the jets from different events and sum it up and average it, or else taking the energy from different calorimeters and sum it up and average it?
So you take all the jets from all the events. So
It is from many events then.
many events.
Okay.
So when you take an average, it's average over many possible jets. This diagram.
So at first you will differentiate what is one prong jet and another one is not two prong jet, and then you averaged one prong jet alone.
So no, it's the other way around. This is first of all out of a simulation. So you can always, in a simulator, let's say through MathGraph or Pythia, you can shoot a gluon, okay, and see what your simulation says about the pattern of energy deposition. Now you can shoot this, let's say 1,000 times. You can repeat the similar experiments for a hadronic decay of W and a hadronic decay of top. So for each cases, you will get some average image. Since you will use such images for the purpose of training a neural network, you first need to understand the data and need to ensure that makes some physics sense. So here, the average image shows that hadronic decay of W has a secondary maxima, which you expect because there are two-prong decays, versus something coming from gluon, which is a one-prong structure. All the maxima is sort of, centered.
Why there is a prime in eta and phi?
Sorry?
Why there is a prime, eta prime and phi prime?
Because these are pre-processed. These are not absolute eta and phi, the coordinates you measure from the calorimeter. You center it around the hardest set. So you sometimes made a coordinate transformation, phi prime equal to phi minus phi max, where max denotes the location where the hardest set was. Similarly, there is an eta prime, which is eta minus eta max. Okay, so that's why there is a relative coordinate shift, which shows in this preprocessed images.
What is ML4 jets? I thought you will tell that.
It's machine learning for jets.
What is 4?
I mean, it's just, that's the fancy way of writing because it's a conference series. Yeah.
But I guess you've also rotated all events, the secondary peak.
Right.
Is
aligning, yeah. Otherwise, every secondary peak on every instance will have a random direction of emission, right? Pattern fragmentation. So now it's rotated. So of course, thank you. It shifted and rotated that for a W jet, every secondary peak aligns in the same direction. If that was not done, what you would have get a secondary circle around this.
So I have a couple of questions associated with that. But before that, what's the difference between the left and the right? You may have said that I missed.
This is coming from gluon, and this is coming from hadronic decay of W.
Good. Sorry, the left one is which?
Gluon fragment.
Gluon fragments. Good. Now, Atlas and CMS have rather sizable magnetic fields.
Right.
Which is going to disperse charge tracks.
Right.
Depending on their momenta.
Right.
But only in one dimension. Presumably, I guess Atlas is a longitudinal field, so it's basically cylindrical geometry,
right?
Correct? So it's only going to disperse it in phi. So jets, so a WDK with a secondary aligned along phi is going to look different in principle. And this is my question. Practice, then if it's aligned along eta, there's no precise symmetry. The question is that important at all? The orientation of the field in doing these kinds of studies? Do you have to account
this
for it?
particular task, it's not, because for a given event, the magnetic field will bend some of the charged particles in a direction and it will form a jet. But then from the eta phi of the jet constituents, you know where the jet is going, the direction of the jet, as well as the relative coordinate. Now,
there's possibility it's going to disperse.
But it won't disperse enough to come out of the cone of the jet.
No, I understand that, but if you want to do precise, just looking at these images,
right?
Because you want to do microscopic substructure in a sense. You want the network to look really at the fine details.
As much as possible.
As much as possible. So. Yeah, if your statement is it's irrelevant, I'll stop asking. But it seems to me at some scale, especially for the gluon jets, at some scale, it should have some influence.
With the current granularity, it's not a big of an influence because what you essentially do, remember, here when we make such jets, we really don't differentiate for this task so much between a forward jet and a central jet. All the jets are brought on the same footing after doing the pre-processing, and then you make an average of the jet images.
So my other question is also, and again, maybe far too detailed and doesn't matter, but pixels are in the calorimeter, you've got a calorimeter cell, it's square and 8 of 5.
Yeah.
But as you're rotating, you have to sort of, pixels don't match onto pixels. There's a rectilinear geometry that as you rotate, you have to sort of interpolate. So do you think
absolutely. So that's why in the realistic task, you never work with jet images. This was done on a simulation where it was a super simple toy imaginative detector where everything of equal grid size and things like that.
Okay.
So, but it was about 12 years ago. It was about making a proof of concept to make a statement that whatever the computer vision people were applying, that can be brought and used to do some hadronic physics.
And of course, if the pixels are small relative to the structure you're looking for, none of this matters.
Yeah. Great. More questions? Good. So now, absolutely for the same reasons, the points were raised that why, in realistic sense, taking an absolute uniform grid sizes are not proper, because here we have different granularity calorimeters, so on and so forth. People thought of we should be moving to point cloud. And that brought us for deploying machine learning on sets. So what is a set? Essentially, if you take this language, if you take the constituents of a jet, it's an unordered set. It's a collection of 4 vectors. So if we ever have to write an inductive bias, a nonlinear function on a set, better we first try to understand how to write a nonlinear function on a set. So let's start that. So what is the property of a function written on a set? First of all, it has to be permutation invariant, which means that if you randomly swap the orders, the output of the function shouldn't change. That's the first criteria. And then there are criterias that how do you construct a nonlinear inductive bias on such sets. The proposal was if you write down a function in this way, that xi's are sort of elements of a set, you act a nonlinear function on this, and then perform a permutation invariant operation. This can be a product, this can be a sum, and then pass it through another layer. This what is called deep sets in the language of machine learning. Okay, it's a permutation invariant operation on the sets. And this turned out to be very useful for the first instance. How it was applied in the world of physics on jets. So this was proposed in 2018 that look, if you construct a function where zi's are the energy fraction carried out by each particle, then by construction, this thing is IRSF. And then you can, people later multiplied by this, by taking some theta I to the power alpha, the angularity parameter, so that now we have a neural network layer which has all the nonlinearity property which you want it to have, but it also satisfies the 2 basic criteria of constructing a jet, which is IRC safety. Okay, this was the first time it was proposed that let's write a deep set model on the constituents of a jet, which is IRC safe. So these were called energy flow network and particle flow network. So what the idea is, you have some particles, you give it, these particles are coming from the jet, you pass it through a phi network, which means for each particle, you have a latent representation, then sort of do a permutation invariant operation to gather the information, pass it through another layer of nonlinear function, and you have some output. Now, how, yes, you have a question?
I didn't mean to interrupt. I'm very familiar with all this
Sure.
field, but the nonlinearity that you're referring to, is there a way to understand physically what it means?
It means.
And what's the origin of this?
Yeah, very good. So let's look at how the function, let's say when we are talking about nonlinear functions here, there is a basic building block, which is called multi-layered perceptron. I will just give you the example of the most simple structure. This is as following. So let's say I have an input x. This can be some, let's remove the vector sign, it's confusing. Let's say this is a number. Now, I perform an operation wx times b. So w can be some rm cross d number, and b is also some rm number. So what output you get is rm kind of number, right? This thing is something belongs to rm. Now, this is still, with higher dimensional numbers, is just a linear transformation. Yeah, absolute linear operation. But now, on linear operation, you add something called activation function. So let me give you the first example of an activation function, which is called ReLU. So ReLU of x is equal to x for x greater than 0, equal to 0 for x less than equals to 0. So if I draw it, here is the function. Now, this is a nonlinear function. Okay. So now you have applied such a filter which is nonlinear. So let's call, if you pass this through a ReLU, then this is a basic construction, and this is my definition of fx. Then this fx is a nonlinear function. Okay. Now, what you do, that you keep doing some stacks of a linear transformation and then a nonlinear activation function. And when you make such a stack, which I may try to draw here, let's say you have a little box here where you have a linear pace pass through a ReLU or some activation function. There are multiple copies, and then again a linear pace, things like that, and then you have an output. So if you give an x, this is called, and if you get some fx as output, these are the structures which are known as multi-layered perceptron. Multi, if you do this little internal stacks multiple times, that's multi-layered perceptron. Now,
it's a nonlinear in a very, very specific way.
Absolutely. And the choice of nonlinearity, remember the nonlinear pieces don't have any weight parameters. Okay. Yeah. And the whole point is it's like an ansatz, a conjecture in the world of, in the literature of computer science, that in infinite width limit, they can perfectly emulate any nonlinear functions in the world. But it's not a hardcore proof. Okay, so that's the statement. Great. Now, when we have that, we sort of constructed the criteria of a function written on sets, but then on top of sets, you can induce another structure, which is connection between the sets. So you take it to one higher order structure, which is called graph. A graph is a set plus some adjacency matrix. So if you write down functions on a graph, there can be a criteria of invariance which can be imposed, which means if you permute this set, the adjacency matrix undergoes some similarity transformation, the output remains unchanged, and the statement of equivariance is if you perform some permutation on X, the output will be changed in a covariant way. That's the whole statement. Like whatever we, the physicists, call covariance, the part in the literature of computer science, they call it equivariance. So some of you who have attended my earlier lectures will find these slides like familiar. Okay. Now, I will just tell you some 2-3 slides about the core structure of a graph neural network, because graph neural networks are the most widely used neural networks currently in the domain of particle physics. So it's not a bad idea to at least learn and get a feel of, oh, you have a question, yeah. Absolutely.
You construct a graph, then it may not be valid. After constructing a graph, that statement may not be valid.
No, the statement is, I build a function in such a way which satisfies such, I build a function in such a way, f, which satisfies this criteria. So these are constraints imposed on the construction of the function.
Fine.
Okay. Now, just let's try to see how they work. So a graph, you saw from the earlier picture, has a bunch of nodes and it has neighboring nodes. So you can gather those information, update the representation at node level, and then try to perform the following, that you can do something called all possible machine learning tasks, either at the node level, edge level, or on the graph level itself. So these are the sort of machine learning tasks you can try to do. Here it says classification, but this is some, the resource I gave you, I took the image from there, but this can be a regression task as well. This can be any downstream machine learning task. The whole point is, if you have such a generalized structure called graph, you can ask downstream for downstream machine learning tasks at node level, edge level, graph level, and it's completely flexible. You define what is the task you want to do, and there is a possible way to construct a nonlinear function which will perform the downstream task. Okay. So depending on the kind of operations you're doing, here you can see that there are, in general, 3 broad classes of graph neural networks we have in market. One is called convolutional, where the sort of correlation number which is used to club numbers from neighborhood nodes is independent of the initial node data. Initial node data here is represented as X. And then there is something like you can club the neighborhood node data, construct an attention score, and you can use that attention score to perform some sort of gathering weight, if you want to call it that way. And finally, there is a message passing neural network where, so first of all, let's remember this attention function is a fixed function. You give an xi, xj, it always returns you a fixed number. But when you sort of elevate this function to the role of a neural network, that this psi function has trainable weight parameters. So if you change the weight parameters for a same given pieces of xi and xj, the output will change, okay, because these are parameterized function. In such cases, these are called message passing neural network. So these are the broad classes of neural networks are in use in the current times, and we will see how they are deployed in jet physics. Yeah. So xi, xj is that, let's say, when you, at least for a homogeneous graph, which means the data structures sitting on each piece of node have identical structure. They are some RD kind of thing. Now, psi is a kind of MLP which has 2 inputs. It can take 2 numbers as input and returns you back 1 number. And when I take, say, number, I always mean it can be some higher dimensional number. It needn't be R. Okay, so psi has trainable weight parameters. So when you will do gradient descent and backpropagation, the weight parameters of psi will change. But nonetheless, it creates a number which sits on the edges, because any number like this little output is a function of I and j, because the input takes I and j label as inputs, right? So any data structure in the context of graph where I are the node labels, then a structure like ij, which is a direct product structure, it sits on the edges. Psi is trainable function. No, xi, xj, for the input, it's the features on the sitting on the nodes. But when you have the output graph, its latent representation has updated. So xi, xj are functions of the weight parameters from the previous layer. But nonetheless, the real weight parameters is a different weight parameter coming from the nonlinear function psi itself. Okay, good. Now, just this is a most generalization. that like in the machine learning schools, we sort of teach how to implement this and how to code it up, etc. But you take it in the following way. If you have a graph by definition has three pieces of data: a global data, an node data, and edge data. And you should see a graph neural network layer as something which takes a graph as input, gives a graph as output. It's just the data sitting on the graph has evolved because it has passed and been convoluted through weight parameters. That's the way you should see. Okay, and then there are many different kind of comparison. So this is like a full graph neural network block where you give input a graph, get output a graph. The message passing neural network is what I described to you, and also the depth set. So it's just like iterative information propagation. So this is an example of a modern day graph neural network. This was a particle net, and this is called, this uses the idea of dynamic graph network. Why? Because a little hconf block, which you see here, it actually takes, if like there are particles sitting on 3D space having some coordinates, it takes the coordinates as well as the features sitting on those nodes. So now all of those informations are used, and on the second part, this data has been taken and used as a coordinate. Now, let's try to appreciate this, that the coordinate which is used here is output from the first block. So the coordinate representation have evolved. And inside this little block, we are again performing some k nearest neighbor algorithm to reconstruct the graph. So the graph structure, the adjacency structure itself has evolved, and thus each time you're passing a graph to one of the blocks, it's not only the data sitting on the graph has evolved, but the adjacency structure has also evolved. So this, in that sense, is a dynamic graph neural network. Okay, and
Graph means that you have connected all the particles in some manner.
In some manner. So that's the k nearest neighbor algorithm. So now you have to decide what is a distance metric. So typically what people do is that take the eta phi coordinate and compute the Euclidean distance. And now you have the Euclidean distance, you can ask, given a particle, I will connect my 5 nearest neighbor kind of thing. So that's the KNN algorithm. Good. So now, when we have such networks, of course, people try to innovate many such general classes of algorithm, and you can see that different algorithms which were sort of popular. Let's say this was the scenario 2-3 years back. People were trying, and people were asking that, look, if I have some energy deposits on the surface of a calorimeter, and if I throw it to a neural network, can I classify all this? And all such classes of networks which are popular in the domain of high energy physics, this is exactly for jet tagging class. And I want to clarify that when I say jet tagging, tagging is a downstream labeling task. You can use the similar kind of architectures, neural networks, for some regression task as well. You can ask, yeah, you have a question? Yeah.
Yeah. This all works great for pure data, for LEP data, E plus E minus, where every hadron you want to associate with the jet. Hadron colliders are a little messier. Your collisions are not nearly as messy as my collisions, but nevertheless, there's underlying event, there's some kind of cleaning that needs to go up. Is this all done by hand ahead of time, or is there some functionality that you can build in that can kind of clean for underlying events?
So there are functionalities which have been proved to work for pileup removal. Okay, so pileup removal is essentially a node classification task in the language I was telling. Why? Because if I have a jet here, I should have hard scattered particle, like depositions here and there, but some soft clusters which are coming from pileup contamination. So if I form a jet out of this piece of sets, then it's my task to identify which set of nodes are coming from pile-up vertices. So this problem was solved around 2020.
So you've been talking about 4 vectors, but there can be sort of information about event vertices, information about timing.
Absolutely, I will come.
This is all encoded.
In such class, but then I will exactly come to the issue that how do you throw the information of cracks and try to do the vertexing inside a jet, maybe the primary vertexing, all these issues. So
One also, right. Secondary vertex within a jet is very interesting as well.
I will
Okay, good.
talk in great details about this. Okay, so now, since this turned out to be the particle transformer, sort of quite popular architecture, it won't be a bad idea trying to understand how it works. So those of you who have done a little bit of machine learning must be familiar with the transformer architecture. And the core at the heart of the transformer architecture is something called attention mechanism. What it does is that if you have 3 pieces of data, Q, K, V, which is created from the input data through some linear transformation, then what you perform is the scale dot product attention. This is the stuff. So you have Q, K transpose, these 2 of vectors. Then there is some mixing matrix. For the time being, you can ignore the detailing of U, and then you sort of make multiplication, matrix multiplication with V, and you pass the whole thing through a softmax. The softmax is again another nonlinear activation function. And then you keep stacking all such blocks and try to perform some downstream task. So this is something called particle transformer. Just for the information, that transformers are like real building blocks of all these large language models and things like that, which we see. We will have some discussion later. But nonetheless, if you really want to understand how machine learning on jets are done on the modern days, what you do is these particles, which means essentially the features of particles inside the jet, you sort of show it to a trained neural network and ask it to perform a downstream task where each of this particle attention block is this sort of like complicated internal structure. So this is something you have to code, build up, and deploy. Okay. So in order to show you, like when it was around 2021, 2022, this became one of the leading architectures. These are the set of node features which I'm talking about. All this X sitting at each node. What are the possible X you try to use when you try to perform a good downstream task on jets? So just let's look at this. It contains kinematics, but it also sort of have the particle identifications. And then if there are associated tracks, you then start like putting in the perigee parameter of the tracks in order to identify how much it has bended, things like that in the magnetic field. Okay. So now comes my favorite topic, which you also said, which is heavy flavor tagging. And what is so unique about heavy flavor tagging? Heavy flavors have secondary vertices inside a jet. So this is like a cartoon I have made to demonstrate that, let's say there is a B hadron, which came out of the hadronization of a B quark. Then, on an average, you remember that B hadron is not a unique particle. It's a family of particles. On an average, it has a lifetime in its rest frame of 1.5, 1.6 picosecond order of. So when you sort of see that what is the lifetime measured in lab, you do sort of a time dilation, little relativistic correction, and it lives for some time. And it decays to a D meson. Okay, so this is the like hadronic transition of B to D, the Feynman diagram. And then D further decays to K pi, and even the kaon can decay. So these are all heavy flavor mesons, etc., which decays. And all this lies inside a jet. So what really distinguishes a heavy flavor jet from a light flavor jet are the presence of these secondary vertices. So for us, the experimentalist, it's very important we identify and characterize the properties of these secondary vertices lying inside the jet. Now for us, in 2020, the great question was, can we develop a machine learning algorithm when you give me a jet, I can able to tell you that whether or not there is a heavy secondary vertex inside a jet, and if there are, what are the properties of that secondary vertex? So the question should be very clear, what we try to ask. Now this is of course a non-trivial task because there is no one single line formula which will tell you what the answer to this set of questions are. Okay, yeah.
In practical terms, do you actually have to catch the D, or is it sufficient just to see the displaced K pi? Because catching the D it really compounds the difficulty.
No, actually we never catch the D.
Right. You only look at the displaced.
So if K on decays, so probably we will get some K long here, some lepton, some pion. That's what we will catch in the calorimeter. And
so you never try to get the tertiary D.
No, so we reconstruct D.
Sorry?
We reconstruct D. We never catch D.
Right. So you don't use the D for tagging.
No, we don't D.
Okay.
Yeah.
That sounded very difficult.
Yeah. Okay. So now, so tau, average tau, so B hadron is a family of particles. Each of them has its own lifetime, which are slightly different from each other. You take some average, okay? And then the beta gamma tau is what you measure from lab. Great. So now, the whole idea was, you take the tracks associated with the jet, and then train a neural network to reconstruct the secondary vertex inside a jet. This we can of course do in simulation, because in simulation we have all the truth sort of information that what the secondary vertex was, which was the particle, how much the displaced amount, etc. So we sort of tried training a neural network. This is 2021. And this became what is called GN1 and GN2 in Atlas, the mainstream tagger inside Atlas. And this is heavily used. And now the whole fun question is, what are the actual practical physics implications of such classes of network? We construct neural networks, we try to train them, so on and so forth. Are they at all useful? So of course, identifying heavy flavored jets, distinguishing them from jets coming from light pattern fragmentations are important, but how efficient they are and what are the physics utility, that's something we will see. So you try to see from this graph, this is roughly at a particular detagging efficiency. You compare that from the previous existing deep neural network based tagger, how much was the enhancement because of this new set of architecture based on graph neural network. And once this was sort of confirmed, it's working pretty well, let's look at the physics impact. This, I will spend one slide telling you one of my favorite physics topic, which is Charm-Yukawa and Higgs self-interaction. So here you see that we are trying to put some upper limit on cross-section. So those of you who don't know what does it mean, 95% confidence limit, upper limit on some parameter, don't worry. Take one statement away, that when we say we have observed something, this number, signal strength, comes down to 1. 1 means observation, and upper limit is any number higher than 1. So and this is also an old plot, like 2022, and now numbers have even improved. But the statement is as following. When in 2015, this number was around 120, which means we were still way away from observing a charm interacting with a Higgs, second generation Yukawa coupling. Once we developed this neural network and deployed and measured on data, this number came down to close to 20. This was just the effect of a smart neural network. And now this number, combining all the different data, etc., has come down like 3. Okay, the latest plots roughly if you see. So, I mean, before the era when LHC was turned on, the statement, like the understanding was, even if we observe Higgs, the best we can do is to measure mass and probably watch or probably discover the third generation Yukawa coupling. At that time, let's say in 2008 or 2010, no one had this courage to say, we will definitely observe second generation Yukawa coupling. But now we know that after this, when the phase 2 run starts and we do all the data analysis, that is sort of guaranteed. We will observe second generation Yukawa coupling. Similarly, the statement goes for Higgs self-interaction. So I'm not showing you the plots of Higgs self-interaction here, but there are analysis which tries to see whether or not there are two clean on-shell Higgs production in the final states. And this is a very interesting process for us. Proton-proton goes to 2 Higgs plus something. This final state gives us the probe of Higgs self-interaction. And that the status of such analysis is also that we never thought we can actually measure Higgs, like we will observe 2 on-shell Higgs production in the final state. But here, like if a Higgs decays to BB bar or CC bar, things like that, we can reconstruct them so well using this sort of modern graph neural network that this is now within our catch. Like next set of data, which will come, let's say 4 years down the line or so, by that data analysis, we will observe these things. So this is truly like observing new parameters, or like not new parameters, I would say, but unobserved parameters of standard model, which we thought we wouldn't, but now we can see, and that's the impact of these modern day neural networks. And it's like it incarnated from the concepts which we use for jet tagging. In fact, Higgs to BB bar is also jet tagging. It's the hadronic decay of Higgs. Okay. Great. Now, people of heavy iron, like this is the paper, took the same architecture which we sort of had taken and applied it. And here, in some simulation of AMPT stuff, which you know better, I don't, for different amount of centrality, applied the heavy flavor tagging within the like heavy ion collision scenario, trying to identify heavy flavor. It worked pretty well, perfectly well. They didn't do any modification to the architecture. They just had to retrain on a heavy ion simulation from scratch. But the whole point is, like, we can now develop neural network as a community which sort of works across varying environments. So that is sort of a nice progress we have. Okay, great. Yes. Sorry? So I'm not exactly sure, like they good question. I just the lesson is quite competitive. I think there were some comments on the like in the description of the figure which I sort of forgot to pick up. Okay. So yeah, but the whole point is, like, in this direction, you start getting the efficiency correct. That's the takeaway message from these slides.
The paper, I just pulled the paper. It's
Yeah.
central lead collision.
Sorry?
I just pulled the paper. They're looking at head-on collisions.
Yeah, okay. Good. Sorry? So the red line is this like centrality. So between green and blue, yeah. So what happened? Yeah, there is probably one more curve on the right hand side. Yeah, you have a good eye. Yeah, good. Right. But I mean, I don't know what that exact curve is. people have also studied similar architecture, what will be their performance on EIC. So AI for EIC is a quite big forum. You should go to their webpage and try to see what kind of machine learning they're trying to do. And they're trying to do similar kind of stuff where they did flavor classification for light pattern jets, etc. But the whole takeaway message is that once you know you can solve a downstream task, it sort of works whether it's a PP collision versus heavy ion collision and things like that. You just have to retrain your architectures. And I will finish this part by telling you that the current best working model is something which is done within the CMS collaboration that take all the decay modes of Higgs, be it hadronic, be it leptonic, and try to sort of throw everything to a grand, big transformer architecture, which is called GLOPAR-T. Okay, and it takes this many number of input features. You don't need to read it, but the whole point is that it's now sort of proof that if you have a transformer architecture where you throw all possible data available and train it well enough, it can perform all classes of jet tagging together, be it hadronic mode, be it leptonic mode. Okay, good. Yeah.
Can you go back? I was maybe busy downloading the paper. Go back to the kind of performance plots. Not the IC, maybe for your particular PP, not even heavy ions. Let's go back to PP.
Just tell me where to stop.
Yeah, well, I just, maybe I'll ask generically. So, okay, fine mechanism, but there are, people have been doing B tagging for some time now without neural networks.
Absolutely.
So maybe on the slides, perhaps you can comment on what advantages are brought by this approach. I was also thinking about, and it triggered at the heavy ion case. A B tag, you've got a big wash of mess, but it all comes from a primary vertex. You're looking for a secondary vertex. Kind of the details of the background are sort of less important. You're looking for a displaced vertex. So I can see well how this works in heavy ions. There are heavy ion tasks for kind of primary production where these kind of neural net approaches may fail because you cannot model the backgrounds. So my question is really, do you have some kind of compact message about where the advantages of this approach really lie compared to conventional approaches that people have been using now for decades?
Yeah, the conventional approach like System 8, etc., which were at least in LHC community, which were used for B tagging. After you have tagged B jets, if you look for the secondary vertex resolutions, okay, those are the numbers which have significantly improved with this advent of new machine learning algorithms. So the whole point is that if there are additional secondary vertices inside a jet, you can now you give me a snapshot of a jet, which is like a 3D object in space, and I can tell you very precisely where the secondary vertex are, what are the mass of this reconstructed secondary vertex, what are the transverse displacement between the secondary vertices if there are more than one secondary vertex inside jets, so on and so forth. These questions can be answered with much higher degree of numerical precision with these methods. Okay, good. Yes.
So when the complexity increases, I would assume that this kind of nonlinear network should work well. But
yes.
In your lead-lead collision at central collisions, performance was not so good. Why is that?
First of all, I don't know. I just took the paper, but I think they just tried to utilize the model and show that this sort of architectures work. I don't think they have done sufficient careful babysitting of the training. That's my first impression by looking at the paper, but I may be wrong. I need to read the paper in greater details. It's just that they took our paper and used the architecture. Okay, good. So now I will slightly discuss very briefly that in the context of jet, when we, the experimentalists, work, something which we really need to do is the reconstruction, which is particle flow. What is the statement of the problem? Let's say I do a raw measurement. There are tracks, there are calorimeter energy depositions. I want to construct the reconstructed particles, which will play the placeholder for truth particles in my analysis, in my measurement of hills. So in CMS side, there is something called machine learning based particle flow. I won't go into detail, but the whole point is if you give like all the pieces of tracks and calorimeter informations, you can get back charge hadrons, electrons, photons, so on and so forth. So here are the performance plots. And we sort of performed and did a concept that if you really want to have reconstructed particle flow candidates, which should be synonymous to truth candidates, probably you should go for higher order connection between a jet and not a binary connection is enough. So that's where we sort of went through a architecture which is called hypergraph, which we have built, and it, like I won't again go into detail, but it sort of works pretty well, beats the performance of regular graph neural network. And this lets us enter into a new let's say paradigm of topological neural networks, which we are now trying to apply within the context of jet physics in broader sense, like data structures of high energy physics. Okay. So now I have talked a lot about classification, regression, and things like that. But now there are other classes of machine learning approach and tasks which are called generative models. So let's try to see what is the question which we try to ask there. The question is rather simple, but it's profound. Let's say I make certain observation. I have data points. They have some internal correlation, and the data is distributed according to some grand probability distribution function. I'm looking into a stochastic system. However, I don't know what that probability distribution is. Given such a case, can I do sampling? Where I want to sample from a probability distribution where I don't know the underlying probability distribution. So, but I still want to make samples out of it. So that's essentially is a hard problem. How do I do that? That's the core question of the domain of neural networks, which are called generative models. So let's say here we have certain images of human faces. It's all over internet. But now, if there is a pattern which is there among these images, and I don't know, can I do a sampling from such probability distribution? So first, these are the tasks of generative model. What are those? You show a generative model, some real images, and then you try to train a neural network where from the latent space, the information will be encoded, and whenever you want to generate an image, you sort of change one of the noise bits, and which means essentially a random number bit, and it generates a new piece of data set. The whole point is that the output artificial data set will be following exactly same probability distribution function as the real data set. That's the whole task. Okay, so there are class of generative model. These are very important for many domains of physics, cosmology, so on. Like wherever you really want to, like what are the utilizations of those, I will come into play. But I just wanted to show you there are many families of this. One of these are called normalizing flows, where you sort of try to map a distribution to a distribution by making a little piece of transformation at each stage through invertible functions. And that is special because in general, neural network layers are non-invertible functions. So here you pay special attention to construct such neural network layers which are invertible functions. And then there are cases of diffusion models, which are very modern day architectures, which you try to apply some sort of noising and then sort of denoising through certain probabilistic functions, and the probabilistic distribution functions are neural network themselves. Those are parameterized functions. So in this lecture, I don't have time to tell you in details how each piece of such class of neural network works, But nonetheless, it's sufficient for you, at least for this lecture, to know that there are these families of generative model which are very popular, useful, and we use them, all of them, to solve all the downstream tasks to produce samples in the context of jet physics and high energy physics in general. So this is just a comparison, like there are adversarial networks, autoencoder, flow-based model, diffusion model. There is another very new set of class of model which are called flow matching, so on and so forth, but they're there. But now, why we care about? Like, we generate jets, we generate calorimeter showers. The whole philosophy is, if you ask in high energy physics, like let's say if we take the world of our experiments, where the most of computer power goes, the lion's share goes to generate simulations which we use for our analysis. So now, if there was a magic way that we don't run our simulation for days and months and so on and so forth, but rather there is a faster way, you plug a switch and then you have the produced samples which are absolutely reliable, which is fast, and you don't need to spend so much money and time for computing hours. Then life is really good. Okay, so the classes of generative models which we are talking actually does that job. And right now it's doing quite successfully, which we will see. So it all started in 2017, like in our world, when the calogan was proposed. So in experimental physics, like making these Giant showers are like really, really time-consuming processes. So that was proposed to be bypassed through some generative model. Okay, and then we have many different versions and things like that of such generative model. You can understand it's sort of blowed. And here is the money plot I would tell you to pay concentration. So here you can see that these are actual simulation which the black dots takes hours to actually make. These are Giant-4 simulations. But then these are like fast simulations which have something like Higgs to gamma-gamma simulation, which are perfectly emulating the actual Giant simulation. So physics performance-wise, there is no loss of performance. So where is the gain? The gain is in time to produce such simulations. So you can see that more the energy of this. You have a question? Yes, there's a question in the back.
With the matter are popped in, right?
Right.
And in this case, how do you get your machine learning or this method, those information from?
So you remember that we said how we train a generative model. First, you have some real samples. So we already have Giant samples, which
so
encodes all.
You use Giant sample for the training. And
remember,
then you build on that.
Absolutely. Okay. Remember one takeaway, that if a neural network has not seen some data pattern, it cannot do any task on that data. So
but the fact then Giant will be used, but not all the time. You train it, you build your model, and then the rest of your time, instead of Giant, you use the model, right?
Exactly. So the more precise way to state that, you can produce a small Giant sample. Yes. Relatively small Giant sample, which takes probably 2 days instead of 3 weeks. Now use these 2 days of Giant simulation to train all the neural network, and then that trained neural network is sufficient and capable to produce all the Monte Carlo samples, the simulations, which you need for rest of your analysis. Okay. And that's very fast. The comparison of time.
Sanmay,
yes.
Maybe one comment.
Yeah.
Yeah. Sometimes it may not be very useful in a case like when you have QCD, for example. So QCD, we don't trust, say, Monte Carlo, because there are pathological events which mimic signal, and they are not part of the simulated samples at all.
Right.
So if you use, say, simulated samples and train, you will probably not get those pathological events.
So
and if it's not covering all phase space.
Yeah, so there has to be an added comment that Of course, in our any analysis or cases where actually our statistics is so low that there can be some little fluctuation and we can't trust our Monte Carlo estimation, that's where we go for data-driven background. So those are the cases. Analysis by analysis, you will always perform data-driven way to estimate the yields. But nonetheless, where the bulk of the simulation goes is producing like Monte Carlo statistics at very large. Those are the cases definitely you can gain on CPU hours. And that's the real gain which I'm talking about. Yes.
Maybe one additional query. Like, I don't know if I missed it already. So since if you are able to fold in all the effects of through Giant, which basically those are the detector effects, so then eventually you should be able to unfold also, right, through these methods. So in that sense, all these correction methods and everything can be done through these methods.
So the unfolding method you're talking can also be done through a trainable network as well.
Okay.
Yes. Here, can you bring the mic?
It would be useful to have the concept of an uncertainty for a generative network. So you can, if it's a meaningful uncertainty, you then know when your training sample is enough and you can stop because you've gotten the precision you need.
Right.
So is there some concept of uncertainty? How do you implement that?
So first of all, the requirement of uncertainty is not only on generative model, but is any downstream task we do on machine learning. If we do a ROC curve, we still don't put an uncertainty band on the ROC curve. So if we choose a working point, a classification point there, we don't know how to propagate the uncertainty because of our choice. Now, there in the machine learning world, there are the classes of Bayesian network and other networks, which gives us a prescription to sort of estimate the uncertainty coming from the training itself, not the size of the training sample, but the fact that we have reached an optimal set of trained parameter through some gradient descent method. What is the amount of systematics infused because we are using such process? There are prescriptions to estimate uncertainties due to that from the computer science world, but still in our domain, in the broader domain of particle physics, those sort of uncertainties haven't made much sense. So people have tried to utilize those. So still, like as a community, we are not putting a very precise uncertainty on our downstream numbers which we are extracting. So since we as a community are like very sensitive towards numbers which we quote as uncertainties, we want to be careful that we understand what we are quoting as uncertainty. We are still not at that place.
I mean, one could actually do it operationally. We just take the impressive gallery in upper right.
Right.
And you've got average CPU time for the GAN and for the standard. What if I just use, a tenth of the training set? What would the guys look like on the upper right? And you can just phenomenologically extract some jitter.
Right.
So are the GANs optimized in that sense? If I would only use a tenth of training set, would this look terrible, or in what sense is this optimized?
I won't say a rigorous optimization analysis has been done in that sense.
Has or has not been done?
Hasn't been done. So what has been done is that we always match, okay, I have some bulk statistics which are generated samples, see if the summary statistics match the original simulation. And if it does, within a certain amount of like little uncertainty, we are sort of satisfied. And then what we really care about this gain. So as long as the summary statistics are falling on top of each other from the real samples versus the generated samples, that is the kind of accuracy which we want to match. But if you ask me, given a piece of generated sample, like is there a prescription to sort of draw an uncertainty band on top of that? It's still missing from our community per se.
I mean, ultimately it's important because you You've got finite computing resources, you have
Yeah.
to know how best to allocate them.
Absolutely.
And the question is whether you do many moderate statistics calculations
Yeah.
or a few high statistics calculations for the same resources.
Yeah,
There's a very important optimization to be made.
absolutely. I do agree.
Question.
Yeah.
So since this reduces CPU time, so this can be used for Bayesian analysis for extracting parameters, right? Or do they use it? Because you do not actually have to do the simulation, so you can emulate them and find the
Yes.
fit parameters.
Yes,
So
you can.
that's done, right?
Yeah. Okay, I will just now that we know the sort of concepts, we also have attempt towards not only generating the lower level calorimetric showers, we also made an attempt to sort of generate the particle flow candidates itself using generative models. So it's like solving two tasks at one go. So just if you give me truth particles, I just want to bypass this step of generating showers and then again apply a computationally expensive running the reconstruction algorithm. I really want to generate some fast particle flow candidates. That was also being attempted. And these are all inputs to jets. Okay, in that context we are talking. Oh, that's, so when you have a number to number, you can compute an Euclidean distance. But let's say you have a set, two pieces of set. Now, how do you compute a distance metric between them? Okay, so that's where Hungarian loss comes into play. Yeah, I don't know what's the source of the name, but it's like you give me two sets which have different cardinality, two sets with different number of elements, and can I compute a distance parameter between two sets? That's the Hungarian loss. Great. People are trying to do some interpretable neural network, which is still it's not at a mature stage. So this is like a trained transformer, and people try to see that at different layers of transformer, what kind of sort of connections a transformer learns. So it was attempted in this paper, just as a side comment, that for a boosted top tagging, for leptonic top decay, it was found the emphasis the net transformer is giving more on the leptons, but for hadronic top decay, it's giving equal sort of importance to all the subjects of the top. So people, this sort of analysis where interpretable neural networks and what physics is learning, it's still at a nascent stage and it's still developing. Okay. Now, for the last 15 minutes or so, I would like to discuss where things are evolving now. So to summarize, first of all, like yesterday, we learned what are jets. Then we sort of figured out that if you want to do downstream tasks on jet, why it's actually analytically non-tractable and why we are trying to do machine learning on jets. Today, we sort of went through what are the popular architectures. So first, initially, when we started with CNNs, etc., it showed some promise. Then we sort of made a phase transition, went to GNN, and then this plethora of GNNs, etc., which evolved, people came up with many different ideas and architectures, tried to solve similar kind of problems. And now, after, let's say, 5 years of this gameplay, we sort of are in a situation where we know which sort of architecture which works, what are their performance, what are their limits, so on and so forth. And we have sort of solved, let's say, classification, regression. I'm not showing you examples of self-supervised learning and so on and so forth, but those kind of tasks are also done. But nonetheless, we know that these classes of architecture sort of represents jets best. Now, what are the upcoming next frontiers? For experimental purposes, we actually, all we were doing, once we have jets, we were doing some downstream machine learning tasks on them. But now we want to deploy them at our trigger level. And why? Because the way trigger works, you can see how much the rate reduction of trigger happens, which means once we collect data, we have an L1 level trigger, high level trigger, then offline reconstruction. This like downscaling of the size tells you that we actually throw away a huge amount of data which we can't store in real time. We just can't do analysis on them. So if there was a way that we can utilize a bit more of the data using machine learning, extract information from them, our life should really become better in that sense. So for that, people are trying to bring this machine learning methods at trigger level. Now, trigger level is all about fast decision making because our collisions are happening at 25 nanoseconds level. And there we have to make very fast inference decision making tasks in order to do some downstream tasks. So for that, people are trying to do and deploy all the machine learnings which were done on the offline level at GPUs. They're trying to bring on FPGA and SX. Now, what are these names? These are new kind of hardwares on which you have to rewrite your code from scratch. The way you write the codes are absolutely different, but you need to deploy the same kind of architecture. So this is actually a non-trivial challenging task, and people are trying to do that. So here, when you have such 1,000 order of particles, within 25 nanoseconds, how do you do a fast machine learning at that fast speed? So for that, what people try to do is that they use a low latency, which means you have a piece of code which is doing a bunch of ML tasks. You break up into very simple problems. So the kind of architecture you can deploy are pretty simple, but nonetheless, for that, on this new kind of hardware, you can do sort of fast machine learning. And then you do something as pruning, quantization, and parallelization. So these are technical way of how the steps you take for deploying machine learning on FPGA level. But the whole thing is that you sort of reduce your precision based and you try to maintain similar performance. There are technicalities there. Yeah.
Can you go to saying here level 1 trigger?
Level 1 trigger.
Order of let's say 1,000 kilohertz. So that means what you are trying to say that you want to access or process event with even faster than that.
So I want to process these events so that I want to do machine learning inference tasks which match this rate. Right now I'm doing machine learning here where my inference task takes order of 1 second.
So all the machine learning will be, this fast machine learning will be applied to this 1,000 kilohertz rate.
Right, L1 level. That's the target.
And your DAC should also work on that order.
Sorry, what?
DAC,
yeah. So here we already have some amount of data gathering because we do L1 triggering and things like that. So that like hardware level trigger, like some electronic signals and things like that. With that, we want to do machine learning.
Okay.
So people already are trying to see if that's doable. In fact, it is indeed like the deep set architecture which we talked about. People try to see, can we do a jet tagging at level 1? And indeed you can. It's just like carefully, patiently writing down and deploy the similar piece of codes. And there, like people have also tried to see what kind of features are most important for different kind of tagging tasks. So like whether the PT, the particle ID, the like hadronic component in a particle, etc., which kind of, like these are analysis of Shapley values. So what kind of features are used even at level 1, people have tried to see. Great. Now, the most modern frontier is something which is called foundation model. So let me spend a couple of minutes to describe what it is. Like all of us try to sort of see something on Gemini, like ChatGPT kind of thing. I personally use Claude Pro and things like that. All of us can ask different questions to an LLM depending on what our need is. But nonetheless, given that millions of people are asking different classes of question, one cannot train a model for all these different kind of questions. So what, like BERT kind of thing, which was done for the latest frontiers of large language model, it was the foundation model, where the idea is, like, for all possible tasks, you first try to pre-train a foundation model, which will be like a mother of all models kind of thing. And then, depending on your necessity, the task, you try retraining the model a little bit with a given piece of data and perform your task with a better amount of accuracy. So this was sort of done for the large language model. And people ask that can that be done for high energy physics as well as jets in particular. Now, why that is important for jet? We already saw that for jets, we are doing many different downstream tasks. We are doing classification of flavors, we are doing mass regression, we are doing secondary vertex reconstruction, we are doing generative model. So if you think of what are the all possible classes of downstream tasks, and this is being done for Atlas, CMS, the theoreticians, heavy flavor groups, all across. So if there can be one great model for the machine learning on jets, which acts as a foundation model on which you can try to do all possible downstream tasks, that will be a sort of breakthrough. And people are trying to bring the ideas from the domain of large language model to the world of jet physics. Okay. So here, what the idea is, like, you sort of train all possible data you have. Use the most low-level data where I have tracks, hits, muon chamber information, etc. And this you do it for data from different colliders. You sort of make a great jet foundation model, or in general, a HEP foundation model, high energy physics foundation model. And then try to do all possible tasks, which I tried to sort of address one by one. You see, there are tagging, there are particle flow, jet energy correction. So when we say we are trying to do jet analysis in whatever physics context, inside an experimental collaboration, we do all such sort of things. Okay, so if we can have a great foundation model which can try to do all these things, that will be fantastic. So how people are just sort of progressing? So the one which is in the market right now is called OmniJet, or there's a variation called OmniJet Alpha, where the jets are represented as tokens. So the whole idea is that if a jet has n particle, you sort of represent it as an initial token, a final token, and there are n number of tokens inside. Now, how this tokenization works is a little technical. I don't have time, and this is like a bit involved, but nonetheless, once you tokenize the jets, and once you can write down a foundation model, you can use one model for jet generation, which is a generative model, classification, so on and so forth. So the whole idea, like, I really invite you to read the paper and try their codes, which are public. So here is the tokenization of a jet. And then once you have trained a foundation model, how do you gain? This is like, if you have to start every model from scratch, you see what is the sample size you sort of require and how slow the performance growth. But nonetheless, if you have a backbone model, which is coming from foundation model, and you try to do a retraining on top of that, which is like the transfer learning, you sort of start gaining the performance very soon. So that's the advantage. Like, if you have a foundation model which you're starting with, you can do a little amount of pre-training, a little amount of transfer learning, and reach competitive amount of performance rather than taking a model and start training it from scratch. So that's the advantage of foundation model. This is being tried in the domain of jet physics as well. And this will be, I think, with advent of more progress in large language model and their associated foundation model, this will grow Okay, and in our world of high energy physics, in general, these methods are being tried very fast. But I would also say it's not only us, the high energy physicists, cosmologists, like molecular simulations, everyone is trying this. So this is really worth knowing. Yes, yes. So you take like samples from different detectors and try to mix them. Yeah, so the whole point is like a grand model should see all possible data as much as you can. And then on top of that, if you have a new piece of data or simulation, you perform some downstream tasks without much training yourself. That's the whole point. Great. So this sort of brings me towards end of this lectures. So what we should take away from this? So already probably like what has happened over the last decade, we can say machine learning, and of course I didn't discuss anything about how much machine learning is used in also things like lattice and things like that. So where people are trying new methods for sampling, etc. But in our domain of at least experimental high energy physics, like machine learning is there like intricately everywhere, and it's going to stay with us. So we are trying more and more about this uncertainty estimation, interpretability, etc. And what I think is that there are huge scope of future research and development for this. Like you have your own domain expertise, but you can apply machine learning, and not only apply, you can sort of build machine learning in your domain. So we should talk and exchange ideas with computer science people, which already people are doing, and talk to other branches of science, how they're doing machine learning, so on and so forth. So yeah, that's sort of the finish of the lectures. So I just want to make a little advertisement that every year we perform ML in HEP school. It started from here in 2023. In 24, it was at IOP. Last year, it was at IISER Kolkata. This year, it will be in TIFR Mumbai. So if you guys are interested, apply. The website will come up on the somewhere, TIFR webpage probably. And yeah, that's it. Thank you.
Thank you, Sanmay. Question?
Yes. Yeah.
I want to come back to your the level one trigger. Could you put that back up? Yeah. So machine learning has been discussed really for decades in terms of triggering, and it maybe recently it's developing, but the challenge, it's on the top line, how to cut the rate.
Right.
You've got enormous input, you can't handle it, you got to cut the rate. I can write a one line level one trigger with one parameter that'll cut the rate to whatever you want. It's just a random rejection.
But it's not about cutting the rate.
Well, let me just make my point. So that does the basic job of cutting the rate, and it's unbiased, so that's good, but it's kind of stupid. Just why do you build the accelerator? You're just going to throw the data away.
Right.
So the purpose of a trigger is to keep the physics we're interested in, but in a way, so, and that's by definition of bias. Bias is not bad, they can be good, but they're good only if you understand them deeply in physics terms. And that requires also kind of theoretical reproducibility. And from the detector point of view, online, I don't know, Atlas may be different, but experiments I work on, it takes us a year to finally calibrate the data. Online is the first calibration, we do what we can, but nobody in my experiments ever claims that what's online is the final calibration. We're never going to touch the data again. So you have to kind of build a fence around possible modifications to the calibration. So these are essential features, because once you've thrown away data, it's gone. You're never getting it back again. Never getting it back. So one has to be exceedingly conservative, I think, at this level one point. And that's the reason why a lot of fancy machine learning algorithms that do all kinds of stuff people, at least in my circles, have been very skeptical because of these features that it's very hard to understand exactly post facto what you've thrown away, what the bias is, in other words, and what, whether you're really building a robust fence around possible changes in calibration. So this process has to be physics driven. So can you say a few words about what motivates kind of the next generation of machine learning attack on this trigger problem? Which physics problems motivate that? And how do you address kind of the bias, the calibration issues?
Because we are interested in physics, which has very, very small cross section compared to the processes which we often see in colliders. We want to really probe rare physics. And there is a good amount of belief that we are throwing away so much amount of data that we are really losing our expectation values on such rare physics. So we really want to gain.
That's fine, but because you want to do it doesn't mean you can do it.
Of course.
Yeah. So how do you address the bias? Maybe you can give an example.
People are trying to see whether they can try to look for axions and dark matters and things like that at trigger level analysis. So these are really rare physics, which is swarmed by our QCD background, whose cross sections is quite many folds higher. And then people are trying to see, since we just have more data here, can we just do our machine learning analysis at trigger level so that our probability or expected number of events for such very rare processes can be increased. So that's sort of the motivation.
So for these very rare processes, maybe the issue is the difference between discovery and precision measurement. For discovery, if you have a bias, well, okay, you can live with it.
Yeah.
But eventually you want to do precision measurements. Maybe there's a spectrum there as well.
Right, but this is where it's completely open field in terms of R&D. We haven't reached the best ML activities there, but ultimately we somehow want to put our hands on the data which we are throwing away until now. So yeah, that's the motivation.
Yes, Sanmay, on this note, I just want to say, actually, we need more advanced electronics to capture all these events.
Sure. So
then trigger level, we are triggering.
Sure. So I must say that this machine learning and etc. is never bypassing the detector and instrumentation development. It's on top of all the technological developments. Okay, so the more that side is absolutely crucial. It has to be there. But now, nonetheless, whatever you can achieve by making latest and greatest technological advancement in terms of hardware, machine learning has the promise to make your life better on top of that.
And I have another question. So all this machine learning we did based on some previous knowledge.
Previous knowledge?
I mean, training the parts. So it mainly model how you start with.
So if you're thinking about we are doing on simulation, now there are methods of self-supervised learning,
yes.
Right? So that is also done these days quite heavily, at least people try it on jets, that if you're given a jet sample, even from data, and if you just do a self-supervised training, can you learn the underlying physics? Yeah. So those are also going on.
Yeah. Sometimes when we discuss new physics, which we don't know, and how to get those new
Of course.
physics.
I mean, if your simulation don't know what the new physics can be, how can it tell you? Yeah, of course. That's a valid point.
Yeah.
Dibyendu has a question.
So a basic question. On your slide 7.
7, let me go back. It's a long journey back.
So you have multiplied by some z in the function f. And you claim that this is IR safety.
Right.
So how can I see that from by
So
multiplying z?
if you add another soft particle, and which has vanishingly small z compared to m number of present particles, that doesn't change the output much. Why the jet angularity variable? Something like summed over I, z I, theta I to the power alpha, where theta is the angle of emission of the parton fragmentation. Why this is an IRC safe observable? This is called jet angularity. because if you add another soft particle, the total sum doesn't change by much. And if you add another collinear particle, since the theta is small, the sum doesn't change by much. So the same concept has been brought here, that you just don't put your neural networks phi here, sort of weighed by the energy emission fraction, which makes it IR safe.
Okay. Like if you have a 10 GB, you are adding 0.001, it will not change anything. So yeah, let's stop and thank Sanmay.
Thank you.
And please discuss with him